continued, getting rid of the batteries. If you look to the EEC test setup, basically it consists of a signal generator, an amplifier, power meters to measure the forward and reflected power, and an antenna. The forward and reflected power meters are typically only used to regulate the field, for example during substitution measurement. The real only absolute reference in the radiated immunity test setup is the field probe. So that's why it is very important that the accuracy of this field probe is crucial. It is as good as possible. Several parameters contribute to the uncertainty of a field probe. I will handle them in a later slide. And very often, isotropic error is not clearly specified. It's really strange because you're using an isotropic field probe and you might expect that the isotropic error is also clearly specified, and not only on one frequency, but over the complete frequency range. Now, we have found that very often this is certainly not clear. If you go to the definition of isotropic response, if you look to the basics of isotropy, people might know the isotropic radiator antenna. This is an antenna that radiates the same amount of power, the density, over its entire volume. And so typically this will result in a perfect square. So it will radiate 360 degrees around in 3D. If you refer that to a field probe, you would expect the same response from a field probe. So a field probe can be defined as good isotropic when it is measuring exactly the same field, independent of its position in the field. And so typically, if you have a test setup where you radiate a field strength, let's say 10 volts per meter, at a certain polarization, and you put the field probe in a specific spot in the middle of this field, and you would rotate the probe around in 360 degrees, so really in 3D, ideally this should give exactly the same measurement result. But in fact, that's not true. And you have to understand that isotropic response is a property of the field probe itself. So only the field probe electronics will define how the isotropic performance will be. If I make a question, what contributes to anisotropy? You can define that a field probe without any error, that's impossible. Every field probe will have an isotropic error. So every field probe will have some parameters that will contribute to the uncertainty, the isotropic error. For example, the difference in between the detectors. If you have a field probe using 3 antenna elements with 3 detectors, these will never be 100% exactly the same. There will always be some difference in between the detectors, which you will also see in the response of your XYZ performance. Specifically, the housing of a probe is also very defining for the isotropy. In the past, we also started with our first laser power probe being a cubical probe. Cubical probe is okay in frequencies, at lower frequencies. The higher you go in frequencies, the sharp edges on the cubical probe will cause resonances, will cause eddy current effects, which will give a disturbance on the field. So it's better to have a spherical probe. A spherical probe, by definition, does not have very sharp edges. But another contribution could also be the probe mount. Your probe has to be positioned in the field in a certain way. Typically, you use a probe mount for this, which is many cases fixed, connected to the probe. This will have some dielectric effect and arranges that the field probe is not perfectly symmetrical anymore. And last, the fiber optic connections, certainly if you use reflective connection parts, these will also give disturbances of the isotropic performance of the probe. All these effects are also quite frequency depending. You will see in the latest slide that at lower frequency, it's all relatively fine. But the sooner you go higher in frequency, the problems start to increase. And in general, you must say that the field probe should have as low as possible isotropic error as possible. And it should also be reproducible, of course. Then you may question, okay, how is isotropy specified? Very often we see it is specified at low frequencies. Sometimes it's a spot frequency, sometimes it's 100 megahertz or 1 gigahertz. But why? Why is it specified at these low frequencies? If you go back to, okay, what is the background of this? At 1 gigahertz, for example, the wavelength of the signal is 30 centimeters. So at 30 centimeters, quarter wavelength, 7.5 centimeters. If your probe size is not in the same relation of the wavelength of the signal, yeah, the anisotropic effects of the probe are neglectable. But as soon as you go higher in frequency, for example, to 3 gigahertz, where the wavelength is 10 centimeters, quarter wavelength again, 2.5 centimeters, when your probe size is in the same region, then you start to see resonances. And it's certainly the case if you have a cubical probe. A cubical probe, I already said before, you will have the eddy current effects, which will also give a disturbance field. So you will see at higher frequencies, the error of isotropy will increase. And that may also be the reason why it's until now it's very often specified at low frequencies. Even there are some manufacturers that specify isotropy as down to 0.4 dB. And we wondered, okay, why do you specify it as down to 0.4 dB? Because typically an error is always specified as worst case, not what is the best you can achieve. But if you calculate with a number of 0.4 dB, that could be quite tricky. So be careful when you are comparing specifications. Okay, then I want to explain more about the different ways of how isotropy can be measured. The first method is what we call balance between axes. Typically, during a balance between axes method, we position the probe in the X, Y, and Z direction into the field, and we will measure the response. And the difference in between these three positions is a number of the anisotropy, actually the imbalance between the axes. This gives some indication of the isotropic performance of the probe, but it's not really the isotropic response, because you're only measuring at the three, let's say, ideal positions. So with the one of the elements exactly in line with the field. If you look to some results, and this is a certificate or a graph from a certificate of our RadiSense 10. The RadiSense 10 is the latest field probe that we have developed, which has 6 antenna elements. In the graph, you can see that over the complete frequency response of the probe, the three measurements, so X, Y, Z measurements, are really on top of each other. So that means that there is no real imbalance between the axes. The correction factor of 1, it should be 1. 1 means that the applied field is exactly the same as the measured field. So this graph clearly shows that it is correctly measuring the field and there is no imbalance in between the axes. As a comparison, I can also show you a graph of a competitive probe. And this is data taken from the public domain, so they have published this on their own website, so it's no secret or no tricky way of showing data. But here you can see a different story. So here you see that 2 of the axes are on top of each other. So the Y and the ZX are almost on top of each other, but the XX, the blue line, is way below. So here you can clearly see that this probe has an imbalance between the axes. Furthermore, you can also see that the isotropic or the frequency response is not completely 1 over its entire frequency range. And then you might say, okay, yeah, if I know the frequency response, I can compensate for that in software. But yeah, that's only for the ideal X, Y, Z positions. What happens in between the axes is unknown. Another way to measure the isotropic performance is by rotating the probe in a horizontal plane. So typically, this could be an anechoic chamber where you have a turntable. You put the field probe on top of the turntable on a probe stand, and you rotate the turntable 360 degrees around. When you then illuminate a field with a certain orientation, for example horizontal, 2 of the antenna elements will be illuminated. and the one which is perpendicular should not measure anything. This is something you can do in your own chamber, but you have to take care of the effects that can happen in the chamber. For example, the influence of objects that may reflect. For example, the table. And you might think these reflections are relatively small. Yeah, we have done quite some extensive measurements which show different. In the next webinar, we will go more deeply into this topic. So for this, I want to skip this. Then the third way to measure the isotropic performance is what we call rotational symmetry. During rotational symmetry, you have of course, you need an anechoic chamber. You generate a field strength with a fixed level and a fixed orientation, for example, horizontal. And then the field probe is placed on a stick, which is at an angle of 54.7 degrees in relation to the applied field. And that's why we call it the magic angle. If you would rotate the stick around 360 degrees, you will see that at each 120 degrees, one of the elements will be in line with the field. And this method gives the best representation of isotropic performance of the probe. At their measurement, or at their products, we have built our own R&D chamber, where we have included a probe positioner. It's an R&D chamber which is completely covered with hybrid absorbers up to 40 gigahertz, so it's a fully anechoic chamber. The probe positioner arranges that the probe can be rotated 360 degrees round at the 54.7 degrees angle, and we have automation software to perform all the measurements. I want to briefly show you a small video of how this looks. The measurements that we have performed in this chamber was from 1 gigahertz to 6 gigahertz in 100 megahertz steps, and we rotated the probe around in 360 degrees at 1 degree steps. So you can imagine that this is a lot of data. I don't want to share all the data at the moment, but I've taken out two spot frequencies, 3 gigahertz and 6 gigahertz, so middle in the range and on the top of the range. This is the performance of our own RadiSense stem probe at 3 gigahertz, where you can see we have generated a field of 20 volts per meter, and not only on the X, Y, and Z axis position, it gives 20 volts per meter, but also in between. So that means by rotating the probe, it continues to indicate exactly the same field strength. So the isotropic error is relatively small, and still we have 0.5 dB as an error. If you look to the same performance of the probe, but then at 6 gigahertz, you will see that there is a slight deviation in the isotropy. So certainly in between the axes, you see some smaller errors, so it's not completely circular anymore. Still at the X, Y, and Z position, it's spot on the field, but in between you see a slightly higher value. Overall, the isotropic error of this probe is 1.6 dB at this frequency, which you might think, yeah, it's not that good, but let's see if we compare it with other brands of probes. We've performed a number of measurements with 3 different manufacturers at the same spot frequencies. So here is manufacturer A, where you can see at 3 gigahertz, it's pretty good. It's also quite circular, so this is good. But if you look at 6 gigahertz, you will already see that there is some more deviation of the performance, the isotropic performance, certainly in between the axes. So if you would look at the positions X, Y, Z, these are relatively the same. So these are okay, but in between the antenna elements, you will see that it will start to give larger errors. At 3 GHz, it was 0.8 dB, but at 6 GHz, it's already 4.3 dB. And this is, I can already say, the best of the competition we have seen. If we now compare other probes, then this is probe B, which was tested at 10 volts per meter. Here you will see that at the X, Y, and Z positions, there's already a difference. And specifically, the Y-axis is measuring more than the other two axes. So there's already an imbalance in between the axes. If you look in between, there's even more differences. Here there's an error at 3 GHz of already 5.3 dB, which is quite substantial. And as I already said before, when I ask customers, many think, okay, 2 dB, but in fact, it's much higher. But if you go to a higher frequency, in this case 6 GHz, then you will see that the difference are even bigger. Again, in between the axes, the differences are huge. If you calculate the isotropic error total, it's 9.6 dB at 6 GHz. So yeah, you can hardly say that it's measuring correctly. The third one is also at 3 GHz. You will see that there, between the antenna elements, you will see some deviation. So again, at X, Y, Z, it's right on top of what the field should be. But in between, it's measuring more. It has an error of 2.7 dB. If you look at 6 GHz, yeah, it starts to go much bad, much worse. Here you will see that it is by far symmetrical. And it ends up in a total error of 9 dB. And so you will see 1.6 dB, 4.3 dB, or 9 dB. That's our major differences. And take into consideration that your field probe is your absolute reference. Now, how can you handle 9 dB of error? That's quite severe. Okay, the question, why is this isotropic behavior so important? I already said it before. The E-field probe is the only absolute reference in your test setup. But you also should take into consideration that a perfect anechoic chamber, meaning without any reflections, yeah, that also does not exist. Even if you radiate a field with a certain known polarization, it doesn't mean that there are no other fields coming from any angle. The chamber itself has to comply to the field uniformity, which is 6 dB. So it could happen that a reflected wave can come from any angle. And if you put your EUT in your chamber, and many EUTs or almost all EUTs are quite reflective. So if you put your EUT in your chamber, yeah, the situation only gets worse. If we then look, okay, what are the contributions to the overall accuracy of a field probe? These are the parameters that contribute to the overall error. Then you have to deal with the linearity of the probe. You have to deal with temperature response. Typically, the field probe will be used in an area of, let's say, between 20 or 25 degrees. The isotropy, of course, but also the frequency response. Then you also, when you calibrate your probe at an external lab, yeah, this external lab also has a accuracy. So this also has to be taken into the equation. And finally, electronics will always drift over time. So also aging will have a small effect. The method to measure or calculate the total uncertainty is what they call the root sum square. So you have to take all the individual parameters, square them, sum them, and then take the roots. And this gives you the number for the total accuracy. And what you might see is, certainly with these errors of 9 dB, that isotropy is very often the most contributing factor to the total uncertainty. If we do the math with the numbers that we have measured, and then we only take the 3 dB or the 3 gigahertz frequency, you will see in a competitive probe, a linearity, yeah, a typical error will be between 0.1 and 0.5 dB. A temperature response, yeah, will have an equally error, also let's say 0.5 dB maximum. The frequency response after compensation can also be half a dB. The calibration uncertainty of a lab, 1 dB, is quite normal. Aging over time, a tenth of a dB. And from this list, you already see that the 5 dB error of isotropy is way out compared to the other numbers. So if you take the root sum squared calculation on these numbers, you will see that the overall error is coming out on 5.1 dB, meaning that the isotropy is really dominating the total accuracy of your measurement. So you can put a lot of effort in having a probe performing very well on frequency response and linearity, but if your isotropy is bad, yeah, it will also give a bad overall accuracy. If you now compare this with our own RadiSense 10, you will see linearity half a dB, frequency response half a dB or 0.1 dB. Isotropy is 0.6 dB. So here you will see that the total sum of this number is much lower. It comes out on a total accuracy of 1.4 dB, which is more than 3 times more accurate. So that's the conclusion, that the isotropy is really an important parameter to take into account and take into consideration when you want to achieve accurate field strength measurements. Then I also want to share some customer experience measurements. Here we have a graph of a test that was done by one of our customers, where he said, okay, I have an anechoic chamber, I have a test setup where I generate a fixed test level, and I repeat the measurement by using 3 different types of probes. So in basics, you would expect that these 3 probes will give relatively the same measurements performance, because nothing has changed. It's the same chamber, it's the same test system, it's the same settings, everything is the same, only the probe is different. And what you can see, it's quite interesting here, is that in the frequencies, let's say up to 3 gigahertz, the 3 probes are really relatively giving the same reading. But above 3 gigahertz, they start to spread. The variation in between the 3 probes is quite severe. At some point, one probe is almost giving more than 100 volts per meter, while the other one is measuring below 30 volts per meter. So this is a huge difference. And yeah, there's only one explanation for this, that it's really the isotropic performance. At 3 gigahertz, the isotropic error really starts to grow, and this then contributes to a completely different field strength measurement. We come to the end of my presentation. So the conclusions. We can say that isotropy is the most dominating E-field probe parameter contributing to the total uncertainty of your field strength measurement. You can also say a little bit different, when measured differences in field strength are mainly caused by non-isotropic behavior of field probes. And that's what we have seen in the last graph. The isotropic behavior gets worse at higher frequency, and therefore we think they also should be specified over its entire frequency range, and not only on the single spot frequency. And rotational symmetry measurements, they give the best indication of what is the real isotropic performance of a field probe. And you have to take into consideration that when you have a field probe with a very poor isotropic performance, you can make wrong measurements. So you can have unjustified approval of your chamber, but you can also do over-testing or under-testing. When you test UT at 10 volts per meter, or at least you think it's testing at 10 volts per meter, but in fact it's testing at a much lower field level because of the error. Yeah, you're under-testing your EUT. That's, of course, not what we want to achieve. This comes to the end of my presentation. I heard that at the beginning we had some problems with the sound, so I hope that you excuse us for this. But there is now some time for question and answers. I have here one question which is raised. Have you also done any kind of measurements in the reverberation chamber where the field is intrinsically isotropic on a statistical basis of higher frequencies? Yes, I can say we have done measurements, but this is also a topic for next webinar. So during this next webinar, we want to go more into detail on these results. So sorry, you have to be patient. I have another question here. Could correction factors of field change over time? Yes, of course. Typically, a field probe needs to be calibrated like any other measurement device at a periodical basis. Normally, it's 1 year. Certainly for an absolute reference instrument, 1 year is a normal period of time. If it would drift faster over 1 year, there should definitely be something wrong with the probe. But typically, we would say every year you need to calibrate your probe, and during calibration, not only the isotropy is measured, but also the complete frequency response of the XYZ positions of the probe, and also the linearity is calibrated. One of the questions is that the RadiSense has a damage level of 1000 volts per meter. Does this occur immediately after applying this field, or does it take time? Yeah, if you illuminate it with a field strength higher than 1000 volts per meter, yeah, there is a severe risk that you will damage the probe, so that there will be a defect. So yeah, please don't do that. That's the advice. Another question, is there any plan, action in the standards, for example, the IEC 61004-3 to include isotropy? Yeah, that's a very good question. Unfortunately, I don't have the answer, but I think it would certainly be a good idea. Because everybody is using isotropic probes already, yeah, as I said, since decades. But if you look at how well has this isotropic error been specified, or what were the requirements, no, there is no real number. They only say you need an isotropic probe, but if it said, if it is isotropic is enough that you have a probe with 3 antenna elements, if that's the definition, yeah, then you can have a big error. So I think it's certainly a good plan, and yeah, if we can contribute to that, we will certainly do. That this is also taken into the standards. I have another question. If we properly add the correction factors, the calibrated data of each direction X, Y, Z, and use it to calculate field, would it also improve the isotropic symmetry? It will have some positive effect, of course, but the frequency response and the isotropy are two different parameters. In the RadiSense 10, perhaps interesting to explain, we have the capability to store the XYZ frequency response data as user corrections in the probe. So the reason for doing that is that it's easier for the customer to use the probe for measurements, because typically until now, mostly these correction factors were applied in software. Yeah, but in software you can do it wrong. You can swap the axis, or you can, yeah, there are different ways that you can do it wrong. So in the RadiSense 10, we have the capability to store the XYZ, so the 3 individual frequency response curves, into the probe. And then when you use it for isotropic measurements, it already automatically calculates with these factors. see if we have. I think we have more questions than I can answer, but do our best. There's also a question here, what is the mean factor of isotropic error over 3 gigahertz? At 3 gigahertz, we already said that the error is above, let's say, half a dB. At higher frequencies, like 6 dB, yeah, we specify in our leaflet. So in our leaflet, we have the specific isotropic errors over the entire frequency range of the probe. And yeah, I can only underline that this is something which should be done in the industry in total. Yeah, but if we look now, very often our manufacturer or our competitive manufacturers don't specify over the entire frequency, but only at one spot frequency. And again, very often it's also a very low frequency, which is not giving the real number. The question here is, do you have same test data with magic angle for NARDA, AR, or ETS? Yeah, we do have this, but yeah, our policy is to share this in a, let's say, neutral way. So not calling the brand names, but calling it competitor A, competitor B, competitor C. So we have this data, but we don't share it by name. We have another question. According to the MIL standards 461, it is necessary to use each X for radiated susceptibility, RS103. I have to be honest that I am not 100% clear about this. But if the question is that you measure it with one X only, yeah, this is something you can program. You can configure in your software that you also only want to measure one X. And which X this should be, yeah, this is to the decision of the engineer. No. Okay, I think we are at the end of the presentation. On behalf of their products, of course, I want to thank you for your attendance. If you have any questions or you need further information, yeah, of course you can contact us, send us an email, call us. Of course, you can also contact your local reseller or visit our website. I hope it was interesting, and I would like to see you in our next webinar in the near future. Have a nice day.